Our project is on system design of a knee motion sensor to prevent ACL injuries. Team members are Tobani Azdani, Tony Petro, Anas Al-Harbi, and Salima Secondary. Our work was based on foundational work of BAS from 2015 and 16 team, which they have worked on one accelerometer and one flex sensor on a Arduino board, and our prototype includes one Arduino board, 3-axis accelerometer, 2 flex sensors, 2 pressure pads, and excessive testing. But what is an ACL? A stands for anterior because it's placed in front of the knee, C for cruciate because shaped as an X, L for ligament because it's the band of fibrous tissues that connect bones together. But why are ACL injuries so important to us? First, there are every year between 100 to 200,000 ACL injuries happening only in the United States. Female athletes are 2 to 8 times more likely to suffer from an ACL injury. ACL does not heal on its own, and the surgery is very expensive. It can be up to $50,000, and there is a very long recovery which can take up to 9 months. The problem is, despite the large number of studies being done on identifying ACL injuries, there is still 1 out of every 13 female NCAA athletes which sustain an ACL injury, and there is no system in place quantifying the strain on the ACL in order to prevent injuries from happening. Now, looking into the knee joint anatomy to understand the knee motion, there are 5 major components: bones, muscles, cartilage, tendons, and ligaments. Ligaments are one of the most important parts in the construction of the knee, which includes medial collateral, lateral collateral ligaments, which are the 2 ligaments on 2 sides of the knee, posterior cruciate and anterior cruciate ligament, or ACL, which is the ligament that we take a look into for this project. Basically, ACL connects the top bone, which is called femur, with the bone on the bottom, which is called tibia, together, and prevents tibia from moving forward from femur. Now, there are 2 types of motions that cause ACL injuries. We have non-contact injuries, 70%, such as rapid change of direction or sudden stop, and we have contact injuries which take into account of 30%, which can be a direct contact or collision, such as a football tackle. Now, looking into the equations of the motion of the knee to understand the forces being applied on the ACL. So there are 6 different forces being applied to the knee. We have foot force, shank force as transmitted forces. We have 1 external force, the ground reaction, which is when the person's foot is on the ground. And we have 3 muscle forces, quadricep, hamstring, gastrocnemic. And also, it's important to understand that sum of all these forces is equal to tibial shear force, which is the force shown in the color of red. And also, the angle between the y-axis of the earth and the y-axis of the shank is called shank angle. Now, this tibial shear force, or TSF, that I mentioned is the force that actually causes ACL injuries, and is equal to 2100 Newton plus and minus 50 or higher. Now, looking into Newton's second law, sum of the forces equals the mass times acceleration. So looking into the equation of TSF, we have force of shank plus foot force, ground reaction force, and we're subtracting all the muscle forces at the end. Now, the solution is to create and implement an knee motion sensor that shall provide real-time situational awareness for the athlete by first using inputs retrieved from sensors and convert them to usable data. Then those data is going to be plugged into the TSF equation to estimate the TSF, or the strain that is being placed on the ACL. If the strain is elevated, then the person is going to be notified by the system. And also, the athlete and coaches are able to look at the data, which is stored in the system, for a post-game analysis to see basically which movements are going to be dangerous for the athlete. Looking at some of the mission requirements, such as the system shall alert the user when the TSF force is approaching the warning threshold, and the system shall calculate the strain on the knee with an accuracy of no less than 85%. Looking at the functional description diagram, we have two inputs, mass of the user and height of the user, to estimate the mass and height of the shank. Then the other inputs into the system are acceleration, shank angle, flex angle, and pressure, which are all going to be used in the TSF equation to estimate the TSF force, and then this force is going to be compared with the warning threshold. In case if the force was higher than the threshold, it's going to alert the user. If not, no action. And also, all the data is going to be archived. Looking into circuit diagrams, we have all the sensors on the left. We have MUX, which basically allows us to use multiple sensors. We have the Arduino board, the micro SD card on the top, and lastly the battery and LED, haptic, and audio system to alert the user. Looking at the Arduino and MATLAB interface, we have the Arduino code on the left, which basically includes the TSF equation, which all the data is going to be plugged in. And on the right, we have the MATLAB code and the interface where the person enters the height and weight. Looking at the phases of development, we have the first phase, which basically includes the calibration of the sensors. The second one, using the CAD to print the 3D printed cover for device. Looking at the phase 3, the open cover look of the circuit, and phase 4 is a variable sock, which includes the device and 2 flex sensors, 2 pressure pads, and the 3-axis accelerometer. Looking at the system test plan, there are 4 different phases, which include testing on the pressure sensors, flex sensors, accelerometer, size, and the weight. All of those are going to be tested based on the mission requirements, which were derived, and their objectives. And as you can see on the last column on the right, we have the results. As you can see, we were able to pass all the different tests that were done on the device. Here is our final results. As you can see, this is the tibial shear force, which is compared between the 3 different activities: walking, running, and jumping. This is a very good way to compare how high the TSF can be during each of the activities. Now, looking at the market opportunity for our device, there are 2 main markets for the KMS device. We have US athletes, which includes NCAA student athletes. We have previously knee injured individuals, which includes knee joint ligament tears, and the total number can be up to 50 million individuals only in the United States. Now, looking at cost, we have recurring costs with a total of $650,000 plus minus 20, the startup cost with a total of $300,000 plus minus 20, and our component cost, which is $180. Now, looking at the net present value, we have 2 scenarios, optimistic and pessimistic. And looking at the return of investment, we have $26 million for the optimistic and $16 million for pessimistic for net present value. We have 89% for optimistic and 73% return of investment for pessimistic. Here is our management team. We have Taban Yazdani as a project manager, Tony Petro as lead engineer, Anas Al-Harbi as test engineer and systems integrator, Slima secondary as marketer, budget analyst, and test engineer. For our future work, we would like to miniaturize electronics, incorporate muscle forces, and also perform the field test. Thank you.